Welcome to Advanced Data Analysis 2 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at the assignment for Class 7 on randomized complete block designs. Now, in this assignment, we are going to look at 4 statistical designs, and the fourth one I'm actually not going to tell you what it is, and we're not going to actually use it. But I want you to start thinking like a statistician and brainstorming sources of variability and how to control for those. So I'm just downloading our Markdown file for Class 7, setting the working directory, and knitting the document, and we'll read through. While this is going, let's take a look at a quote from Ronald Fisher, the father of statistics, basically. He wrote, "To consult the statistician after an experiment is finished is often merely to ask him to conduct a post-mortem examination. He can perhaps say what the experiment died of." The main lesson here is that in designing an experiment, it's important to get the statistician involved at the beginning, because both the design of the experiment and the analysis of the experiment are the same. Basically, they're the way you analyze it depends on how you conducted the experiment. And if you made bad choices at the beginning, it may be that you actually cannot learn anything from your experiment. And in this assignment, we're going to look at 4 statistical designs. The first one is one such scenario where you can't learn anything. We are going to iteratively improve that design in designs 2 and 3, and then in the fourth one, we're not going to analyze it, but I want you to start thinking about like a statistician and see if you can come up with an even better design to control as many sources of variability as possible. So in this assignment, I'll introduce you to the experiment that's being conducted. We'll say what design 1 died of, and then designs 2 and 3 we will analyze the data, and design 4 you brainstorm how to do even better. Alright, so tire wear experiment. I'll make this a little bigger. A fleet manager wishes to compare the wearability of 4 brands of tire. We'll label them simply A, B, C, and D. 4 cars are available for the experiment, and 4 tires of each brand are also available, for a total of 16 tires. The idea is to mount 4 tires on each of the 4 cars and ask the driver of each of the cars to drive his or her car for 20,000 miles and then measure the tread loss. So I guess we're actually taking a measurement at the beginning and then after 20,000 miles measuring it again and looking at the difference. We will measure tread loss in mils, which is thousandths of an inch. We will designate the cars simply as C1, 2, 3, and 4. All right. So, brands are randomized to cars. So here's a very simple diagram. C1 is car 1, and there are 4 tires on car 1, and the brand label indicates where those tires are on the car. And I do not have a specific designation here, but maybe this is like the front left, front right, back left, back right. In everything that we're going to talk about in this assignment, we don't really talk about the tire position. Though, hint. Okay, so that's the structure of this design. Now, what is the obvious flaw in this design? And I do have a link here. Perhaps I'm giving too much away, but if you think about it a little bit from the statement of the problem, 4 cars are available. Okay, now we don't know what those 4 cars are. They could be the same. They could be very different. Also, there are drivers, and drivers are probably not going to drive the same way. Some will drive on the highway, some will drive on city streets primarily, some may drive on dirt roads. So there's several sources of variability here. And so I want you to think about, well, we'll go to this link in a second. Think about why this is a bad idea. Here we've randomized brand A entirely into car 1. Okay, so some thoughts here are basically you can't really separate the effect of the brand A tire on its tread wear from the type of car it is, the type of driving that is being done, the types of road surfaces that the car is driven on, possibly other things. So let's go look at this obvious flaw link. So this brings you to a page on confounding, and I really would like you to read a little bit about this. In particular, read this summary at the top. Read this definition here, and I want to scroll down a bit to the types of confounding. Now, I scroll down. Here we go. So we've got three. So confounding variables may be categorized according to their source: the choice of measurement instrument, operational confound; situational characteristics, procedural confound; and inter-individual differences, person confound, are the three types here. And I believe that this is a procedural confounding, and it can occur in a laboratory experiment. This type of confound occurs when the researcher mistakenly allows another variable to change along with the manipulated independent variable. So the manipulated independent variable is the tires, right? We want to understand how the wear of tires depends on the brand of the tires. So that is what we're manipulating here. And then the other variables that are changing are the cars and the drivers and the types of road surfaces, those things like that. So I believe a good answer to this question is that the problem is that we have procedural confounding, and I would like you to define a little bit about what that is and why it applies to this situation. All right, design 2. Excuse me while I get a sip of water. So this is a better design, a completely randomized design. We will see a little bit later that we can do much better, but let's analyze this design and see what the results are and see why we might be able to do better. Another design that negates the confounding is to use a completely randomized design. It entails numbering the 16 tires, 1 through 16, and then drawing at random the numbers and assigning tires to cars in a completely random manner. So, for example, we'd have our 16 tires, sort of labeled 1, 2, 3, 4, 5, 6, and so on, right? So, and then randomly choose those values. So we're gonna fill in on each of the cars. We're gonna fill the positions with tires from them. So maybe we draw, a number. Let's see, number 10, number 2, number 16, number 14, number 1, number 4, number 5, number 9, etc. And we just fill all the positions on all the cars. So that's not too bad, right? Now at least we've randomized tires to cars. That randomization is removing some of the inherent bias of systematically putting all of one tire onto each car. All right, on the right-hand side, we have the actual wear. Okay, so this is 12 mils, 17 mils, and so on. And we can analyze this data. That's what we're going to do. Okay, so what I've done is we don't have any files to read this time. Because the data sets are small, I'm showing you a way to read text directly from a script file. So we library the tidyverse and bring in the ADA functions for the diagnostic plots. Here is the data. So we've got the 4 cars, C1 through C4, and then we have those actual values below there. And I'm using read.table and specifying that we're going to read the table as this text that starts here. We have an open quote here, and we have a closed quote here. And everything between those quotes are the data. And I'm specifying that we have the header equals true, that these should be treated as column names. Similarly, we have the treatments, TRT for treatments, and that indicates what the tire brand is that is associated with each of the where values up here. Now I need to bring these 2 files together. So the first thing I do, and I should go over to RStudio to walk through some of the code here because it's handy to see that. So let us do that. Go over to RStudio. Let me scroll down to where we start to read this data set in. Okay, so I've just read in D2 means the data for example 2, and we have DAT, so we get this little table, and D2 TRT is the treatment. Okay, nice. So we've got those 4 square, or those 2 square data sets. It's going to be much more useful for us to be in long format. So what this next piece of code does is it's going to take the data object and pivot longer. It's going to take the column headers and turn that into a column, and then it's going to take all these values and put all the values into a column. So pivot longer says I'm going to use all the columns. The names, meaning the column names, are going to go under a column called car, and the values in the table are going to go under a column called where. So let's just run that part just right here. Okay, so we take the data and we pivot longer. I'm going to highlight that and press Control Enter. It will submit just that piece of code, and we'll see what that does. All right, nice. So we've got the car column with the car 1, 2, 3, 4, 1, 2, 3, 4, etc., and then the where values. So we just stacked the data vertically. And then the last part here is I'm going to mutate to make car a factor variable. So rather than it being a character string. So now I'm ready to run the whole thing. Let's take a quick peek at this object. And at the top here, you can see the car is now a factor variable. I don't actually recall what it was before, but it used to be a character string. Very nice. So now it's the way we need it. We do exactly the same thing for the treatment data set, but now instead of where we have the values are the brand, A, B, C, and D. And the brand is going to be a factor variable right there. So I'll run that, and we'll look at D2 treatment long. And we've got car and brand, both factor variables, all the cars and the factors. Perfect. So finally, because these are in the same order, we can now bind the columns together between these 2 data sets. So that's what I do here, and I've got D2 all, and I'll also print it, but we've got the car, the where, and the brand. Oops, I put caps lock on. There we go, car, where, and brand. Okay, seemed like a lot of work to get such a simple table, but it is better to write code like this and be proficient at this type of writing code, because there will be times when you have a large data set and this code works regardless of how big the data set is. All right, let's keep moving. So I think we can go back over to here at this point. All right, so the appropriate analysis for this experiment is a one-way analysis of variance. Right, this is chapter 5 from Data Analysis 1. So let's just calculate the means since we're looking at a difference in means, so we're taking all the data, we're grouping it by the brand, A, B, C, and D. We're summarizing it, and for each brand, we're going to calculate the mean wear over the 4 tires, and going to assign that to M for the mean. We'll ungroup it from the group, and then these are the means, M, right? So that was all assigned to M.D2, and so these are the means. So it looks like the most wear is on brand A, and the least wear is on brand C. We can create a plot of this, and let's see. Yeah, so we'll go back and look at the code in a second. Scroll out, just zoom out just a little bit. Okay, so along the horizontal axis we have the brands, A, B, C, D. Vertical axis we have the amount of wear. The dashed line here is the grand mean of all the observations. We've plotted 4 points for each brand, so those are the actual wear values, and the symbols and colors indicate which car they're on. We have the mean of the 4 values as the red diamonds, and we have a 95% confidence interval for each of these. I love this plot because it gives you so much information. Right? So in the analysis of variance hypothesis, the null hypothesis is that all the means are equal to each other. And so that this grand mean line is useful to sort of gauge where these red diamonds should be if they were all equal. It looks like there's some variability here. These confidence intervals are pretty wide, though. They do not indicate the result of a hypothesis test. But so we'll soon figure out whether we've got enough variability or enough signal here to indicate whether there's different wear depending on the brand. I want to look at the plot code briefly because there is a lot of stuff going on here. I can see that I commented out a box plot thing. Box plot's not very helpful when you only have 4 observations, right? A box plot is a 5-number summary. It is the minimum, first quartile, median, third quartile, maximum. But we only have 4 observations. So don't summarize 4 observations with 5 numbers. Use a box plot when you've got samples of 10 or more or so. Okay, anyway, so what do we have here? We've got brand on the X, wear on the Y. That's good. We have this horizontal line, which is the grand mean. The y-intercept is the mean of all the wear values. And I'm just making that a dashed line that's very thin. Then I plot the points, and the car and the shape and the color are based on the car, and I've jittered them a little bit along the width, so horizontally. I have not changed the height of the point, so that their position on the y-axis, the actual wear values, is correct, but the jitter horizontally allows them to not, right? So I jitter these points horizontally, so that these 2 points, for example, the triangle and the square, don't sit on top of each other. Now, there's no guarantee that they won't sit on top of each other because the jitter is random, but it helps. Then we've got the stat summary. So here we've calculated the mean for each group. And yeah, just making a point. I like this shape. 18 is a diamond. The reason I like a diamond, I think I've described this before, is because the corners, the left and right corners of the diamond, give you the actual value of the mean visually. Whereas a circle or a square, it's harder to see where the middle is. And then stat summary gives us our confidence limits. So here, the function that we're plotting is the mean confidence limit of the mean using the normal distribution. And the geometric object to represent it is the error bar, which is the red vertical bar with the feet on each end, and it's red. And after that, I give it a title and label. Okay, so a lot going on, but I would say that care is worth it. for a great plot. And once you've done it once like this, you can use this plot throughout your whole career of doing analysis of variances. All right, let's fit the regression model, or that's true, ANOVA is a regression model, but we're going to fit the ANOVA. So where is the numerical y variable? Brand is the ABCD categorical variable, and that's going into fit D2. So first question, are the assumptions for the one-way ANOVA met? Okay, so the assumptions for a one-way ANOVA are basically just that the residuals are normally distributed with equal variance. So we look at the QQ plot. These look beautiful in terms of normality. Observation 12 is sort of an outlier. Not really an outlier, but it's the most extreme negative observation down here. It doesn't look particularly influential. It's hard to tell with only 16 observations. So anyway, I don't feel like this is really super strong evidence that this one should be considered to be removed. Oh, one thing you could add, let me page up here for a second, to this plot. We have enough space where we could put the observation number for each one. And you know what? This is worth a very short detour. So we've got this D2 all object. Let's add to this a variable called ID, and we'll make it the numbers 1 through n, which is n parenthesis is a function which tells you how many observations there are in a data frame. So now we've got this ID column, okay, which is those integers. Let me scroll down here now in the plot, and we can add some geom text. I think I'll do something like this. I'll copy this and geom text, and I believe it's something like label equals ID. I'm sort of flying at the seat of my pants doing this. We're not going to do any jitter, and in fact, let's just sort of take the default, except we'll make them sort of gray. All right, we'll run this plot and take a peek. I am getting a message here. Yeah, that fun y is deprecated. Use function instead, and that's coming after the stat summary. So when I first wrote this code, that was the syntax. So we can correct this as well. On this stat summary line, I'm going to remove the .y. Okay. So, but take a look. We've got numbers now, 5, 2, etc., labeled where they go vertically. So if we wanted to know where observation 16 was, wait, was that the troublemaker? I've already forgotten. Page down. 12. Okay, where's observation 12? It's this one. Okay, I can see why it's such an outlier. It has a huge distance from the other three within this brand B. So that one just did not wear very much. Great, now we have some insight as to why 12 was influential. Okay. All right, so let's check the model assumptions. That's what we're doing. Notice over here on the leverage by Cook's distance plot, Cook's distance, right, is the same axis as Cook's distance here. But now we're asking whether Cook's distance depends on leverage. But look at leverage. All these values are on the same position on the x-axis. That's because our x variable, the brand, is a categorical variable. And they're all equally far from the mean. There's really no mean of a categorical variable. There's no center. So they're all equally far from that. So that's why they all appear to have the same leverage. Residuals versus fitted values, they look fine. Again, here's some box plots which aren't great because we only have 4 observations for each. I think they're not really telling us very much about equal variance. it doesn't really seem like much of a problem here. We have that one outlier down here, observation 12. In terms of transformation, the peak of the Box-Cox curve is close to 1, and 1 is within the black confidence interval dashed lines. The other one's probably over here. So no suggestion for a transformation. Added variable plots also look totally fine. So finally, we have the normality test of the residuals with large p-value. So take some of those ideas and summarize them here about whether you believe the model assumptions are met. All right, so let's test the hypothesis. Can we infer a difference in mean wear between the 4 brands? Here is an analysis of variance table for the brands. We have a p-value of 0.11. So I would, down here, I would state the hypothesis that you're testing and state your conclusion. I'll just say that this p-value is sort of large. Looks like there is not evidence of there being a difference in brands when you use this statistical design. Okay, so let's do better. Design 3, the randomized complete block design. So randomized, we did randomized before. Here we're going to have blocks, which are the cars. Each car we're treating as a block. And the complete means that each treatment is represented in each block. So if we look at this car, car 1, that's one of the blocks. And the completeness is that each brand is represented in that car. We have A, B, C, and D in some randomized order. That's the randomized part. Okay, so just reading here. In this case, each car tests all 4 brands. Thus, one tire from each brand is selected at random and randomly allocated to the 4 wheels on car 1. Then one tire from each brand is selected and the 4 are randomly allocated to car 2 and so on. So here's the result of this design. And these are the measurements. And we're going to read in the data just as we did before. In fact, I'm going to read it in differently just to show another way of laying this out. So here we've got car 1, 2, 3, 4, the wear values, and the brands. So I pre-formatted it into long format. It actually was a little bit easier to do this. Okay, finally we're going to make each of those factor variables car and brand. And we've got our data that looks the same as before. Now I sort of have 2 factor variables, right? Let me page up again. I've got a factor variable for the brand, but we also have a factor variable for car. Now cars are blocks. They're helping us control for the differences between cars and the drivers of those cars. So we want to control for that or adjust for that factor, and then see whether conditional on the types of cars, whether there's also a difference in wear by brand. We're going to see this very clearly when we see the plot. So first, I'm going to summarize this by brand, take the mean for each brand, and I'm also going to summarize, and that's going to be the mean for data 3 brand. Same thing for car. I'm going to create those summaries, group by, and calculate the mean for the wear. And here are the results for the mean brand. Looks like we still have some nice differences here, right? A has the most wear, C has the least wear. But look at these car differences. Car 4, much less wear than car 1. So I'm glad that we're accounting for the cars. All right, so this is the type of driving I did when I was a teenager, and this is the type of driving that I do now as a father. Here's a sort of another way of visualizing the data. I just used the box plot command, and I split the data by by the brand or by car. And we see these differences, at least in median, for example, that center black bar. Okay, so looks like we definitely have differences both in tire brand and in the driving car. So here's the same type of same plot, and this time I've connected some dots. You can see like car 4 is the purple plus sign here at the bottom, and I've connected the dots. The purpose of that is to visually see what the effect of cars is in this plot. And clearly car 4 has the least amount of wear, and car 1, the red dots up top, have the most amount of wear, and cars 2 and 3 are in the middle. So the other additional part here is the geom line, where I grouped by car. So that means that the line is connecting dots within the same car, and the color is also by car. Great. Well, we did a good thing to block by car. Briefly, what relationships are there between wear and brand and wear and car? Okay, so summarize some of the things that we just saw. All right, let's check the model assumptions. The model assumptions are the same for whether you've got 1 or 2 or 3 factor variables over here. It's that the residuals are normally distributed with equal variance, and they're independent of the predictors or things like that. Okay, so are all the assumptions met? Residuals look good. This looks good. We have sort of a large value here. It might be worth, I bet we could probably identify it's probably this troublemaker way down there is observation 15, if I had to guess. That's the one with a wear of less than 8. If I scroll up here, well, I'm going through too much work now. The wear is of 8. That's observation 15. It's the second from the bottom of 16. Yep. Okay, so that explains why that one is an outlier. The leverages are all equal, so no information gained there. The residuals versus fitted looks good. Do these have different variances or not? I think 4 observations is too little information to really tell. These all look fine to me. No need for a transformation of the response variable based on the Box-Cox plot. And now we've got multiple added variable plots because we have 3 brands and we have 3 cars. Or, excuse me, 4 brands and 4 cars. Anyway, but there's a baseline brand and a baseline car within the statistical model, so we only see it for 3 of them here. Anyway, there's no real problems that we're seeing here. There's too little data to make strong conclusions. The normality test shows that we fail to reject normality. So go through and discuss some of those model assumptions here. Now, the big question, can we infer a difference in mean wear levels between the 4 brands? Now, it is appropriate to test whether there are differences between brands controlling for the effect of the car. And this is an additive model. We haven't really talked about interactions yet. That will be in a later chapter. Note that because the car blocks are part of the experimental design, they should remain in the model regardless of whether the block is significant or not. So this term, we're looking at the ANOVA table. Cars are a blocking variable. They were part of the experimental design. Even if cars were not significant, we should include that term in the model because we treated the cars differently in the design. So in epidemiology, they do this sort of adjustment all the time for like age, sex, race, basic demographic characteristics of people. They will adjust for those demographic features regardless of whether they are important for distinguishing or for explaining variance in the response. And this is the same idea here. And what do we see for brand? We do see differences. So we controlled now for cars, and it gave us more statistical power because there was a lot of variability between the cars that we could absorb. And because we can explain the variability from cars, there's less variability in the brands, or less uncertainty about the effect of the brands. So that's great. So draw your conclusion here. I would state the hypotheses, or just the hypothesis for brand, right? The null and alternative hypothesis, and then draw your conclusion. We're going to do some follow-up here. Perform the pairwise comparisons and summarize numerically and graphically. So I've written the code to, I think, to do the numeric and graphic part. The main thing is to interpret this. So we're going to use the EM means package to get the estimated marginal means. We're going to use the linear model object that we fit, and the specifics is we're going to ask if there are differences between the brands. Okay, and there should be two sets of output here. The first one is just the means, each of their standard deviations or standard errors, and the confidence limits. So those are basically if I page up for a moment, what we see in this plot. The mean is the diamond, the confidence limits are the ends of the red, end of the red bars. Okay, so this is not really answering our question yet. It is the next one, pairs, where we look at the differences. So now we're looking at the difference, say, between A minus B. The estimate here is a positive 2. Now this subtraction is in the correct order, so the A wears 2 mils more than B. We have a p-value for that test, and we notice we have a standard error of 0.9. We have a t-statistic of 2.5, and because the estimate is within 2.5 of 0, we don't reject the null hypothesis. So we have a large p-value. But there are some differences here. Looks like A and C looks different, and so on. So I would look through here and make some decisions. Now, just a note, the default adjustment, the family-wise type 1 error rate adjustment, is using the Tukey on a significant difference. Okay, this output can be visualized, and I love this plot. So the estimated marginal means plot is available when conditioning on one variable. Is that entirely true? Anyway, the blue, there's a few pieces of output here. I'll just describe them, but it's worth reading that paragraph that I wrote. So now it's on its side. So the y-axis is on the horizontal now. So this is the means on the horizontal. We have the brands now on the vertical axis. I do this sometimes when I want to take up less vertical space on the paper, because you could make this plot quite short vertically and still get all the information in here. And by having a longer x-axis, you can see in fine resolution like where the differences are. So sometimes putting it horizontally is a nice choice. Anyway, so we've got so going from the bottom up, brands A, B, C, D. So there's the mean for A, the black dot. We have these blue bars, which are the confidence limits. So if I scroll up a little bit, they are from here. Okay, so from 12.9 to 15.5. That's the confidence limit. And then what I love about this plot that I haven't seen anywhere else is you also get these red arrows. Now, you can, just by using the confidence limits, the blue bars, you can't tell whether there is a significant difference based on the overlap of the confidence intervals. That's where the red lines come in. If the red lines overlap, so if you can draw a vertical line and these two lines cross together, then they are not statistically different. So brand A and B, they are not statistically different because they overlap. But A does not overlap with C or D. So A is statistically different from C, and A is statistically different from D. Furthermore, if we draw a vertical line here, brands B, C, and D all overlap, so they're all not statistically different from each other. That result, if I scroll up just a little bit, corresponds to what we saw in this pairwise comparison. A and C differed, and A and D differed, because after adjusting for multiple comparisons with Tukey, the p-values are still less than 0.05. So I love this plot because it gives you the confidence intervals and it gives you a visual way of doing the hypothesis test with the red arrows. Okay, finally, I want you to, as I do in the lecture notes, order the 4 tire brands by their means and then draw horizontal lines connecting those sets of brands that are not statistically different from each other. Okay, so you can, if you want, you can copy this table down here and make some changes. Or you can edit this table directly. I believe that's everything in this section. Yes. Okay, the last part of this assignment is to come up with an even better experimental design than the randomized complete block design. How can this experiment be further improved by design? There are further factors that we haven't considered yet, right? So we've got tire brand, A, B, C, D. That's the main question we're answering. Then we did the randomized complete block design, where the blocks were the cars. I'll page up for a second. Give myself something to point at. Okay, so we blocked for each car. For each car, we have one of each brand on each car. Let's assume that we can't swap the cars between the drivers. Though I guess that would be a legitimate experimental design. Every 5,000 miles, swap the cars around. What else could we do? For example, the main thing that comes to my mind is, where are the tires? And are there locations on the car? I'm not talking about the spare tire compartment, but are there locations on the car where tires should wear more or less? Okay. So let's assume that we're not rotating the tires, though that's probably a pretty good idea to rotate the tires every 5,000 miles or something. But think about another way to improve this. And if you do think of a good way, you get a bonus, so maybe +1, if you can name this experimental design. Okay, so I have something specific in mind here, and I do not really expect you to spend much time going out and finding the name of this experimental design. But anyway, so that is everything in this this assignment. I'll see you in the next one.